Okay, we're going to look at a little example problem of kind of like synchrony and simultaneity, and how do we recognize that as things happen, and if we want to coordinate them across space, moving, and things are moving really fast, we need to take into consideration that there is going to be this delay. So things can happen at the same time, but depending on where you are as an observer, you might not experience them at the same time. So this is no different really than if we are watching fireworks and you see the flash of light before you hear the boom. The flash of light and the boom are happening at the same time. The event is at the same time, but depending on how fast those two different things, light travels faster than sound, it gets to you, the observer, at different times. Okay, so we're going to play with that idea a little bit in an example problem. So in order to coordinate clocks, okay, we're going to coordinate clocks in one reference frame. A light beam is activated at the origin when time equals 0. If you imagine the origin when time equals 0, what time value should be assigned to the timepiece positioned at the spatial coordinates XYZ of 0, 35, 15. And just because I noticed that typo and I'm not going to start over, I'm going to fix it so our video looks good. All right, at least turns into good. Okay, so how do we think about that? So I want to make sure that the clocks are synchronized, okay? And so we're at a position, our XYZ position, of 0, 35, 15. And that's a certain distance away from the origin. And the light flashes at the origin, it's going to take a little bit of time for that light to get to the clock. So how do we assign that timepiece? What is that time difference between the origin and the clock? Well, we need to know how far it is. And so to get the distance from the origin to this location, we of course use the Pythagorean theorem. So the distance to that location is the square root of 0 squared plus 35 squared plus 15 squared. And so that is a distance of 38.08 meters, okay? And so then the question is, how much time does it take for that light to travel to 38.08 meters? So that's just our Newtonian mechanics. Time is our distance over our velocity. Our distance is 38.08. Our velocity is equal to the speed of light, so 3 times 10 to the 8th. So this is d over our speed of light. Okay, and we find that that time difference is 1.25 times 10 to the minus 7th seconds. So 1.25 times 10 to the minus 7 seconds, which is 125 nanoseconds. We often use 10 to the minus 9 as a common, so either one is fine. So this is how much that time value should be assigned to that timepiece. All right, so just kind of getting that idea of that there's a little bit of time difference as light moves. Okay, good job.